Across the largest scales of the universe, the motion of galaxies creates patterns that reveal the presence of a form of matter that does not emit or absorb light, yet contributes most of the mass-shaping cosmic structures. In this outer region, dark matter becomes apparent not through direct observation, but through the gravitational influence it exerts on systems extending across millions of light years. When galaxies move within massive cosmic regions, their speeds and trajectories provide information about the distribution of mass around them. Measurements of these motions reveal that visible matter alone cannot account for the behavior observed. Galaxies travel faster than expected based on the mass detected through starlight, gas, and dust. This consistent mismatch indicates the presence of additional matter that interacts through gravity, but not through electromagnetic processes. The outermost structures of the universe provide clear examples of these effects. Galaxy groups and clusters contain hundreds or thousands of galaxies held together by gravity. The speeds at which galaxies move within these clusters indicate far more mass than the amount accounted for by visible materials. Even when the light emitted by stars and gas becomes carefully measured, the total remains insufficient to bind the cluster. If only visible matter were present, the galaxies would drift apart. Instead, they remain bound with motions that fit the presence of a larger unseen mass distributed throughout the environment. The overall structure of these systems shows that gravity from this unseen mass dominates the behavior of galaxies within them. Dark matter does not gather into bright structures because it does not interact with radiation. It moves through these regions without emitting light, yet its gravitational influence shapes how galaxies fall toward one another or move past one another. In the outer environment of the universe where gravity operates across very large distances, the presence of dark matter becomes necessary to explain how these systems remain intact. Observations across many clusters reveal consistent patterns. The distribution of galaxy speeds the way gas becomes heated within the cluster, and the gravitational influence measured through bending of background light all indicate a mass far larger than the visible content. This consistency across different environments supports the conclusion that an unseen component forms most of the gravitational structure in these regions. The outer cosmic landscape also contains regions where galaxies flow along large pathways shaped by gravity. These flows indicate the presence of massive structures that extend across large volumes of space. When galaxies fall toward dense regions or move away from less dense regions, their motions reveal the pull of mass that cannot be accounted for by luminous matter alone. The large-scale behavior shows that dark matter forms the dominant component guiding the movement of galaxies across these environments. Even the temperature of gas within clusters reveals the presence of additional mass. Hot gas emits light across a wide range of wavelengths, and the temperature of this gas depends on the depth of the gravitational well that contains it. The gas in many clusters remains hotter than would be possible if only visible matter were present. The heat reflects the gravitational influence of a larger mass, and this mass matches the amount inferred from the motions of galaxies. The consistency between these independent measurements strengthens the understanding that dark matter contributes most of the mass in the outer regions of the universe. On scales even larger than clusters, galaxies form into patterns shaped by gravity over many millions of years. These patterns include long bridges of galaxies, extended walls, and large voids with fewer galaxies. The formation of these patterns depends on the amount of matter available to pull galaxies together. Simulations that include only visible matter fail to produce structures matching those observed. When dark matter becomes included, the resulting patterns align with the structures seen across the sky. This agreement indicates that dark matter plays a key role in shaping the largest structures in the universe. In the outer environment, the behavior of galaxies remains consistent with well-established gravitational principles. Gravity requires mass to explain the motions observed, and the mass detected through luminous matter remains insufficient. Because dark matter does not emit or reflect light, its presence cannot be confirmed directly through electromagnetic observations. Instead, its influence appears in the motions of galaxies, the distribution of hot gas, and the bending of background light. Each of these effects aligns with the presence of additional mass that does not interact through light. Uncertainties remain about the identity of dark matter, yet its gravitational influence in the outer regions remains well supported. Measurements of galaxies in clusters and groups consistently show that the mass required to explain their motions exceeds the visible content. These findings arise from observations conducted across different wavelengths using a variety of instruments. The agreement between these methods strengthens the conclusion that dark matter forms the majority of mass-influencing galaxy motions. Even when considering potential sources of error, such as the distribution of gas or the presence of unseen stars, the amount remains too small to explain the gravitational behavior. The need for additional mass persists across all analyses. In these outer regions, dark matter appears as a diffuse component distributed across large volumes. It does not clump in the same way as visible matter because it does not lose energy through interactions with radiation. Visible matter can cool, compress, and form stars, while dark matter remains governed by gravitational interactions alone. This behavior causes it to form extended halos around clusters rather than bright, concentrated structures. These halos shape the environment in which galaxies form, move, and evolve. As the narrative remains within this outer region, dark matter appears as the unseen mass required to explain motions across cosmic scales. Its influence remains measured through the speeds of galaxies, the temperature of gas, and the gravitational effects on light. Although its composition remains unknown, the gravitational behavior matches expectations for a form of matter that interacts weakly or not at all with electromagnetic radiation. These characteristics define the presence of dark matter in the broad environment that surrounds galaxies across the universe. In this initial region, the role of dark matter becomes clear as the primary contributor to gravitational structures shaping the outermost behavior of galaxies. From this region, the movement inward will continue to the next layer, focusing on how dark matter influences the internal dynamics of galaxy clusters. Within the wide cosmic regions where clusters of galaxies gather into dense environments, dark matter becomes visible only through its gravitational influence shaping motions, temperatures, and patterns that extend across millions of light years. In this region, the behavior of galaxy clusters reveals how dark matter forms the dominant component of their total mass. Clusters contain galaxies moving at high speeds relative to one another, and these speeds provide a measure of the gravitational pull required to keep the system bound. When the visible matter within a cluster becomes measured through starlight and gas emissions, the total amount remains far too small to account for the motions observed. The galaxies move faster than they would if only visible matter were present. This consistent behavior across many clusters indicates that dark matter forms the gravitational framework supporting these systems. The galaxies represent only a small portion of the mass, while the unseen component fills the region more broadly. Hot gas in clusters also reveals the influence of dark matter. This gas becomes heated to very high temperatures as it falls into the deep gravitational wells formed by the cluster. At these temperatures, the gas emits light across a wide range of wavelengths. The temperature reflects the depth of the gravitational well, and in many clusters the gas becomes hotter than would be possible if visible matter alone formed the gravitational structure. The amount of mass needed to explain this temperature aligns with the amount inferred from galaxy motions. These independent measures support one another, revealing that dark matter forms the dominant mass in clusters. The distribution of this unseen mass becomes extended and diffuse, surrounding the galaxies and gas throughout the cluster. Clusters often contain complex structures shaped by collisions and interactions. When two clusters approach one another, the galaxies within each cluster move largely unaffected by the collision, because galaxies remain separated by the large distances. The hot gas, however, interacts strongly, slowing down and compressing at the region of collision. Dark matter behaves differently from both galaxies and gas, because it does not interact strongly with other forms of matter. It passes through collisions without significant slowing. The separation between the dark matter and the gas reveals its presence. The galaxies move ahead along with the dark matter while the gas lags behind. This pattern becomes visible through the distribution of mass inferred from gravitational influence and matches expectations for matter that interacts primarily through gravity. The amount of dark matter required to explain these separations corresponds to the mass inferred from the motions of galaxies and the temperature of gas. These collisions provide insight into the behavior of dark matter under conditions not accessible in laboratories. The gravitational lensing of background light offers additional information about the distribution of dark matter in clusters. When light from distant galaxies passes through a cluster, the mass of the cluster bends the light. The pattern of bending reveals how mass becomes distributed within the cluster. In many clusters, the strongest lensing occurs in regions where little visible matter resides. This finding supports the presence of dark matter concentrated in areas surrounding galaxies, but not limited to regions with bright emissions. Lensing patterns often extend beyond the distribution of visible matter, indicating that the mass forms a large diffuse structure. The gravitational influence of dark matter in clusters shapes the orbits of galaxies, the behavior of intergalactic gas, and the bending of light. Although uncertainties remain about the specific nature of dark matter, its gravitational behavior appears consistent across measurements. The amount of unseen mass inferred from these effects aligns with expectations for matter that interacts only weakly with visible components. Clusters reveal how dark matter shapes the large-scale structure of the universe. The distribution of mass in clusters affects how galaxies form and evolve. Dark matter creates deep potential wells into which gas falls, leading to the formation of new stars in some regions. In other regions, interactions with hot gas and the gravitational environment affect the rate at which galaxies form stars. The environment shaped by dark matter influences many aspects of cluster evolution. The large-scale environment of clusters also reveals the influence of dark matter on cosmic flows. Clusters form at intersections of large filaments composed primarily of dark matter. These filaments guide the movement of galaxies and gas-funneling material into the clusters. The presence of dark matter along these pathways determines where clusters form and how they grow. Without dark matter, the structure of clusters would appear markedly different. The gravitational potential created by dark matter also influences how gas cools within clusters. Gas that falls into the well becomes heated and then slowly cools by emitting radiation. The rate of cooling depends on the depth of the gravitational well and the density of the gas. Observations show that the structure of clusters matches expectations for systems dominated by dark matter, even when accounting for uncertainties in gas distribution. The need for dark matter remains clear. The internal motions within clusters reveal additional details. galaxies move along paths determined by the total mass within the region. Their velocities often show patterns consistent with elongated structures or multiple components within the cluster. These patterns reflect how dark matter becomes distributed and how it influences the motions of galaxies. Observations of these motions allow researchers to map the unseen mass. The inferred distribution of dark matter often extends beyond the regions occupied by galaxies, forming a large halo surrounding the cluster. The consistency between measurements of galaxy motions, gas temperature, and gravitational lensing reveals a stable picture. Dark matter forms the majority of mass within clusters, shaping their structure and behavior. Although the exact composition of dark matter remains unknown, its gravitational influence matches the expected behavior of matter that interacts weakly and does not emit light. The behavior of clusters underlines this conclusion, providing a clear environment in which the effects of dark matter dominate visible components. In the outer regions of clusters, dark matter becomes more diffuse, gradually blending into the larger cosmic environment. The density decreases with distance from the center, but the gravitational influence continues across large volumes. This extended distribution helps maintain the structure of filaments and influences the movement of galaxies toward clusters. The presence of dark matter within these regions ensures that clusters remain stable structures over long periods. Although certain details about the distribution of dark matter within clusters continue to be refined, the overall picture remains well established. The gravitational influence observed across many clusters aligns with expectations for a form of matter that interacts primarily through gravity. In this region, the role of dark matter becomes clear through its effects on galaxy motions, gas temperatures, and the bending of light. These independent measurements support one another and form a coherent understanding of cluster environments. From this region, the movement inward will progress toward the large-scale cosmic web, where dark matter shapes the broad structure connecting clusters and forming the framework of galaxies across the universe. Across distances even larger than those spanned by galaxy clusters, the universe forms a structure shaped primarily by dark matter, in which galaxies, groups, and clusters become arranged along vast filaments that stretch across hundreds of millions of light years. In this region known as the cosmic web, dark matter provides the underlying framework upon which visible matter gathers. Although galaxies form the bright points that can be observed directly, their distribution reveals the influence of a far more abundant unseen component. The large-scale structure of the universe did not arise from the distribution of visible matter alone. Visible matter interacts through radiation, allowing it to cool, compress, and form stars. Dark matter behaves differently. It does not emit or absorb light, and it does not cool through radiative processes. Instead, dark matter collapses under gravity into extended structures, forming a network of filaments and nodes that guide the motion of gas and galaxies. As the universe evolved from its earlier stages, small variations in density grew under the influence of gravity. Dark matter amplified these variations because it does not interact with radiation, allowing it to form dense regions earlier than visible matter. These regions became the seeds of the cosmic web. Over time, dark matter collected into long filaments separated by wide voids. Visible matter followed these structures, forming galaxies along the densest regions. The presence of dark matter becomes evident when comparing the distribution of galaxies with the predictions of gravitational evolution. Computer simulations that incorporate dark matter reproduce the filamentary structure observed across the sky. Simulations without dark matter fail to produce structures matching real observations. The alignment between simulations and data supports the conclusion that dark matter forms the primary scaffolding for the cosmic web. Filaments form the connecting structures between clusters. These filaments contain both dark matter and diffuse gas. The density within filaments remains lower than in clusters, but higher than in surrounding voids. Galaxies form along these filaments because the gravitational pull draws gas inward. These filaments represent the pathways along which material flows toward the dense nodes where clusters sit. Observations show galaxies moving along these pathways, indicating that dark matter determines the routes through which matter travels. Voids form large regions with very low densities of both visible and dark matter. These regions expand as matter flows toward the filaments. The contrast between dense filaments and broad voids reflects the influence of dark matter on the distribution of mass. Without dark matter, the voids would appear less pronounced, and the filaments would lack the strength to guide galaxy formation. Galactic surveys mapping millions of galaxies reveal the structure of the cosmic web in detail. These maps show how galaxies trace the underlying dark matter. The distribution of galaxies follows the predicted patterns closely, with large walls, filaments, and nodes forming the key features of the structure. Some of the largest structures observed span distances of hundreds of millions of light-years, consistent with the behavior expected when dark matter forms the dominant component driving gravitational growth. At the intersections of filaments lie clusters and groups of galaxies. Dark matter forms dense regions at these intersections, creating deep gravitational wells. As gas falls into these wells, it heats up and becomes compressed, eventually forming galaxies and stars. The deep wells grow over time as more matter accumulates. These intersections represent the earliest and most massive structures into the cosmic web. The presence of dark matter ensures their stability over large spans of cosmic time. Gas traveling through the cosmic web becomes influenced by the gravitational pull of dark matter. In regions where filaments compress, gas temperatures rise and shocks occur. These shocks influence how galaxies form along the filaments. The amount of gas that can fall into a region depends on the depth of the surrounding dark matter. In regions where dark matter density remains high, star formation becomes more active. In regions where density remains low, galaxies form less frequently. The cosmic web also influences how galaxies cluster together. Many galaxies do not form in isolation, but grow within groups that travel along filaments. The motion of these groups reflects the gravitational influence of dark matter. The speeds at which galaxies move along the filaments provide estimates of the mass contained within them. These speeds often exceed what would be expected if only visible matter were present. The stability of the cosmic web over billions of years depends on the behavior of dark matter. The web grows as matter flows along filaments, yet its overall structure remains recognizable across time. Visible matter interacts with radiation, altering its temperature and distribution, while dark matter remains unaffected by such processes. This distinction allows the web to retain its structure while visible matter evolves within it. The density of dark matter within filaments remains lower than in clusters, yet still significant enough to influence gravitational behavior. The clumping of dark matter at the nodes becomes essential for cluster formation. Without the influence of dark matter, clusters would not form as efficiently or remain as stable. The web-like structure provides the pathways for matter to flow toward these clusters, increasing their mass and influencing their evolution. Observations of gravitational lensing across large scales reveal the distribution of mass along the cosmic web. Light from distant galaxies becomes bent by the gravitational influence of dark matter distributed along the filaments. These distortions provide maps of mass that reveal the presence of dark matter, even where visible matter remains sparse. The patterns align with the filamentary structure predicted by theory. color mapping of cosmic microwave background deviations also provides insight into how matter becomes distributed across the cosmic web. These deviations reveal how density variations grew under the influence of dark matter. The growth of these variations aligns with predictions for a universe dominated by dark matter rather than visible matter alone. Although the exact identity of dark matter remains unknown, its gravitational influence across the cosmic web remains consistent with a form of matter that interacts only weakly with visible components. The structure of the cosmic web arises naturally when dark matter becomes included in models of cosmic evolution. Without dark matter, the growth of large structures would progress too slowly to match observations. The role of dark matter within the cosmic web reinforces its importance in shaping the universe. Its distribution determines where galaxies form, how clusters grow, and how matter flows across large distances. The behavior observed across these regions aligns with the predictions of dark matter models. In this region, dark matter appears not as isolated clumps, but as continuous filaments and nodes forming the largest structures in the cosmos. The motion of galaxies along these structures traces the unseen mass guiding their paths. From this region, the movement inward will progress towards the environments of cluster collisions where the behavior of dark matter becomes visible through the separation between gas galaxies and gravitational influence. Within the broad architecture of the cosmic web, galaxy clusters occasionally move toward one another along filaments of dark matter, and when they collide, the behavior of visible matter and dark matter separates in ways that reveal the distinct nature of the unseen component. In this region, the focus rests on these collisions where the mass distribution becomes rearranged through interactions that affect gas galaxies and dark matter differently. These events unfold over hundreds of millions of years, yet their structures remain visible long after the moment of impact. When two clusters approach their galaxies, drift through the collision field with relatively little direct interaction. Galaxies consist mostly of empty space, and the distances between stars allow them to pass through one another without physical collisions. Their paths become altered only by the gravitational influence of the combined mass of both clusters. The gas within clusters behaves differently. This gas remains hot and diffuse, filling the spaces between galaxies. When the clusters collide, their gas clouds meet head-on, compressing and slowing down as they interact. These interactions produce shock fronts and changes in temperature distribution. The behavior of this gas becomes detectable through emissions across various wavelengths, revealing a slowed heated region at the center of the collision. Dark matter follows a different pattern. Because it does not interact with gas or with itself through forces other than gravity, it passes through the collision region largely unaffected. It does not experience friction or pressure. As a result, the distribution of dark matter moves ahead of the slowed gas remaining, aligned more closely with the positions of galaxies. This separation between galaxies' gas and the gravitational center provides one of the clearest observational signatures of dark matter. Gravitational lensing becomes a key method for tracking mass during these collisions. When light from background galaxies passes behind the system, it becomes bent by the total mass present. This bending reveals how the mass becomes distributed across the collision. In many observed systems, the strongest lensing occurs in regions where the galaxies reside, not in the region where gas becomes concentrated. Because the gas produces most of the visible matter, the separation between the lensing signal and the gas distribution indicates that a large portion of the mass must reside in a form that passes through the collision along with the galaxies. This form remains consistent with dark matter. The difference in behavior between gas and dark matter during collisions also influences the long-term structure of clusters. The gas gradually settles into the gravitational potential shaped by the combined dark matter distribution, slowly cooling and reorganizing after the collision. Galaxies follow orbits determined by the merged halo of dark matter, settling into patterns that reflect the mass of the combined system. These reorganized clusters provide snapshots of the aftermath of collisions. The distribution of dark matter remains diffuse and extended, shaping the overall gravitational environment. The galaxies remain concentrated along the paths established during the collision, while the gas shows signs of turbulence and heating caused by the interaction. Observations of multiple cluster collisions reveal patterns consistent with the behavior expected for dark matter. In each case, the separation between gas and gravitational mass remains clear. In some collisions, the dark matter halos pass through each other without significant disruption while the gas becomes compressed. In others, smaller subclusters reveal similar behavior on reduced scales. These repeated observations reinforce the conclusion that dark matter interacts weakly and remains unaffected by forces acting on gas. The distribution of dark matter within colliding clusters also reveals information about its density profile. As the clusters pass through each other, the dark matter halos distort slightly under gravitational influence but retain their overall structure. The degree of distortion provides information about how concentrated the halos are and how mass falls off with distance. These details help refine models of dark matter distribution. Observations of these collisions also help establish limits on how strongly dark matter interacts with itself. If a dark matter particles interacted through forces other than gravity, the halos might slow during collisions or show signs of scattering. However, in most observed systems, the halos remain aligned with galaxies, indicating very weak self-interaction. Although small uncertainties remain, these observations place strong constraints on the physical properties of dark matter. The large-scale environment of cluster collisions reveals how dark matter shapes the gravitational landscape. The gas shows where interactions occur, while the galaxies show the paths of systems moving through space. The distribution of mass revealed by gravitational lensing shows where dark matter resides. Each component behaves differently, yet the overall picture remains consistent across multiple observed events. Dark matter also influences the growth of structures after collisions. When two clusters merge, their dark matter halos combine to form a larger halo. This new halo becomes the dominant gravitational structure guiding the future evolution of the cluster. The gas gradually settles into this new potential cooling and forming pattern, shaped by the mass distribution. Galaxies within the cluster follow orbits determined by the combined halo, and the cluster gradually returns to a more stable configuration. The outermost regions of these collisions reveal the spread of dark matter along the cosmic web. Filaments connect the clusters before and after the collision, and the distribution of dark matter within these filaments influences how the clusters merge. The alignment of the halos with these filaments helps determine the shape of the merged system. Even after the collision, the influence of the cosmic web remains visible in the distribution of matter. Dark matter appears to retain its extended structure through these events, showing no signs of significant fragmentation. The gas in contrast becomes heated and disrupted, and may take long periods to cool. The galaxies remain largely unaffected except for gravitational changes in their orbits. These differences highlight the role of dark matter in shaping the evolution of clusters. Although the exact nature of dark matter remains uncertain, its behavior during collisions provides strong evidence that it interacts only weakly. The ability of dark matter to pass through collisions while gas becomes slowed indicates that dark matter does not experience forces that would cause scattering or compression. These observations align with models in which dark matter does not interact through electromagnetic or strong nuclear forces. The detailed distribution of mass in these collisions provides further information. In some systems, small substructures of dark matter become visible through lensing. These substructures reveal that dark matter forms clumps within the larger halos. The size and distribution of these clumps influence how galaxies form and interact within the cluster. These substructures also align with predictions for dark matter models that include slight density variations. In regions surrounding the collision, the gravitational potential becomes shaped by the combined dark matter halos. This potential influences how galaxies move and how gas behaves. The overall structure of the merge cluster depends on the mass distribution, which in turn reflects the behavior of dark matter during the collision. Although uncertainties remain about certain details, such as the exact density profiles of the halos, the broad patterns remain consistent. From this region, the movement inward will shift toward the rotation patterns of individual galaxies, where the influence of dark matter appears through the speeds of stars orbiting far from the galactic center. Within the structures formed by the cosmic web, and shaped further through cluster interactions, individual galaxies reveal additional evidence for dark matter through the behavior of stars and gas orbiting far from their centers. In this region, the motions inside a single galaxy show a gravitational influence that cannot be explained by visible matter alone. As a galaxy rotates, stars closer to the center move faster because they remain near dense concentrations of mass. Farther outward, where the visible mass declines, classical expectations predict that orbital speeds should decrease. Instead, observations show that stars and gas in the outer regions move at nearly constant speeds, indicating the presence of additional mass that does not emit or absorb light. This behavior appears across many types of galaxies, from large spirals to smaller systems. In spiral galaxies, bright disks contain stars and gas arranged in rotating patterns. The distribution of visible matter peaks near the center and tapers off toward the edges. If only visible matter created the gravitational pull, the rotation curve would rise near the center and then fall. Measurements reveal that the rotation curve rises and then remains nearly flat. This flat pattern indicates the presence of a mass component that extends far beyond the visible edge. Dark matter forms this component, shaping the motion of stars across the disk. In elliptical galaxies, which contain older stars in smoother distributions, the motions arise from random orbits rather than a single direction of rotation. The speeds of these stars reveal how mass becomes distributed. These speeds remain higher than expected from visible matter alone, indicating that dark matter also surrounds elliptical galaxies. The influence of dark matter in these systems appears through the gravitational binding that keeps stars within the galaxy. Even in smaller galaxies, the presence of dark matter remains evident. Dwarf galaxies contain fewer stars and much less gas than larger galaxies, yet the speeds of their stars remain high, relative to the amount of visible matter present. This behavior suggests that dark matter dominates their mass. In some dwarf galaxies, the ratio of dark matter to visible matter remains very large, reinforcing the conclusion that dark matter shapes their structure. The distribution of dark matter within galaxies remains extended, forming a halo that surrounds the visible disk or spheroid. This halo extends far beyond the region where stars reside, creating a gravitational environment that influences star formation, gas distribution, and the motion of satellite galaxies. Observations of satellite galaxies orbiting larger systems reveal that their paths depend on the mass of the dark matter halo. The speeds and distances of these satellites become used to measure the extent of the halo. These measurements indicate that halos extend far beyond the bright part of the galaxy. Gas in galaxies provides additional evidence for dark matter. In many spiral systems, gas extends farther than stars. The rotation speeds of this gas match those of the stars, revealing the gravitational influence of dark matter at even greater distances. The consistency between the motion of stars and gas strengthens the conclusion that an unseen mass component remains necessary. The internal dynamics of galaxies also reveal the influence of dark matter. Stars within spiral galaxies rotate at speeds affected by the gravitational environment. The presence of dark matter affects how these bars evolve. The thickness of disks depends on how stars move in vertical directions. These motions reveal the distribution of mass above and below the disk. In many galaxies, the vertical motions of stars indicate additional mass that cannot be accounted for by visible matter alone. Even in our own galaxy, the Milky Way, the rotation curve remains consistent with the presence of an extended dark matter halo. Stars near the Sun move at speeds indicating that most of the mass influencing their orbits does not reside within the visible disk. The distribution of star clusters, gas structures, and satellite galaxies reveals the shape of the halo. Although the exact density profile continues to be refined, the presence of dark matter remains well supported. The influence of dark matter also appears in how galaxies form and evolve. During their early stages, gas collapses into regions shaped by dark matter. The depth of the dark matter halo influences how quickly stars form and how gas flows. As galaxies evolve, interactions with other galaxies and with the cosmic web affect their structure. Dark matter halos determine how strongly galaxies attract one another and how they merge. The resulting structures depend on the distribution of dark matter. Even the shapes of spiral arms reveal the influence of dark matter. Spiral patterns arise from density waves that rotate through the disk. These waves become influenced by the gravitational environment, including the presence of the halo. The thickness and stability of spiral arms reflect the mass distribution within the galaxy. Dark matter influences the long-term behavior of these structures. In addition to gravitational effects, dark matter influences how gas behaves in the outer regions. Gas moves through the halo and interacts with the gravitational potential. The patterns of this motion produce structures such as warps in galactic disks. These warps reveal how the outer halo influences the disk. Observations of these features help refine the understanding of halo structure. Although the identity of dark matter remains unknown, its gravitational influence within galaxies remains consistent. The flat rotation curves the speeds of stars in elliptical systems, the motions of satellite galaxies, and the distribution of gas all align with the presence of an extended halo of unseen mass. Alternative explanations must match all these observations, yet none so far align as consistently as the presence of dark matter. The internal behavior of galaxies also reveals how dark matter interacts with visible matter over long periods. The halo influences the rate at which gas falls inward, shaping star formation. The halo also stabilizes the disk, preventing certain instabilities that would otherwise arise. These stabilizing effects influence the long-term evolution of galaxies. The extended halo also influences how galaxies respond to tidal forces. When galaxies pass near one another, the shape and strength of tides depend on the distribution of dark matter. These interactions influence the formation of tidal streams which become stretched across large distances. The patterns of these streams reveal the underlying mass distribution. Observations of stellar streams in the Milky Way and other galaxies reveal clumps within the dark matter halo. These clumps influence the motion of stars within the streams, causing small disturbances. These disturbances provide information about the structure of dark matter on smaller scales. The behavior of galaxies across different environments reinforces the role of dark matter. Whether in dense clusters or in isolated regions, the gravitational influence observed remains consistent with a large unseen mass component. The amount of dark matter within galaxies varies, yet the presence of halos remains a common feature. In this region, the rotation patterns of galaxies provide clear, consistent evidence for dark matter. The influence of dark matter shapes the motion of stars and gas, the formation of structures within the disk, and the long-term evolution of galaxies. Although uncertainties remain regarding the precise nature of dark matter, its gravitational effects remain well supported by observations across many systems. From this region, the movement inward will continue to gravitational lensing signatures, where the bending of light by unseen mass reveals detailed information about the distribution of dark matter within and around galaxies. Within the environment shaped by the rotation of galaxies and the behavior of their halos, the bending of light by gravity reveals the presence and distribution of dark matter with a precision that does not depend on visible matter. In this region, gravitational lensing becomes the primary tool for tracing mass, allowing the unseen structure of dark matter to become visible through its influence on the paths of photons traveling across large distances. When light from distant galaxies moves through the universe, it follows paths determined by the curvature of space-time. Mass bends space-time, and the curvature alters the direction of the light. This bending does not depend on whether the mass emits or reflects light. As a result, both visible matter and dark matter influence the path of photons. By observing how background galaxies appear distorted when their light passes through these regions, the distribution of dark matter can be inferred. The patterns of distortion provide maps of unseen mass that extend across galaxies' clusters and the cosmic web. In galaxies, the effect remains subtle. The bending of light by a single galaxy produces small distortions in background sources. These distortions become averaged across large populations of distant galaxies to reveal how mass becomes distributed within the foreground systems. In many cases, the mass inferred from lensing exceeds the amount of visible matter present. This excess mass aligns with the expected distribution of dark matter in the halo. The lensing signal often extends far beyond the visible boundaries of the galaxy, revealing the full extent of the halo. The strength and shape of the lensing pattern help determine how mass density changes with distance from the center. Observations consistently show that halos extend far beyond the region occupied by stars and gas, forming an extended structure with gradually decreasing density. In clusters, the lensing signal becomes stronger and easier to detect. Because clusters contain large amounts of mass, the bending of light becomes more significant. In some cases, the distortion becomes strong enough to produce multiple images of the same background galaxy, or to stretch the image into long arcs. These arcs reveal the location of dense regions of mass within the cluster. The positions of the arcs often differ from the positions of visible matter, showing that dark matter dominates the mass distribution. The strongest lensing occurs in regions where galaxies concentrate and where dark matter forms deep gravitational wells. The gas which emits light across many wavelengths often becomes displaced during interactions, while the dark matter remains aligned with the galaxies. This separation becomes visible in lensing maps which show where the mass truly resides. Weak lensing provides additional information. When the distortions remain small, they appear only when averaged across many background galaxies. These small distortions reveal the distribution of mass across larger areas. Weak lensing maps reveal the structure of dark matter across clusters and filaments, showing how mass becomes distributed across the cosmic web. These maps reveal that the mass extends far beyond the distribution of visible matter, forming continuous structures connecting clusters. Lensing also provides a way to test the shape of halos around galaxies. In many systems, halos appear elongated or flattened, rather than perfectly spherical. These shapes arise from the gravitational interactions and the formation history of the halo. Lensing measurements reveal these shapes by showing how distortions vary with direction. The shapes align with predictions from simulations that include dark matter. Simulations without dark matter cannot reproduce these patterns. The alignment between observations and simulations supports the conclusion that dark matter forms the dominant mass component. Galaxies with significant dark matter halos produce distinct lensing patterns. In systems where visible matter forms only a small fraction of the mass lensing, reveals halos that extend further than the luminous components. These halos influence how neighboring galaxies move, and the lensing signal confirms this extended distribution. In some cases, galaxies with little visible matter show lensing signals that reveal a large unseen mass component. These systems provide strong evidence for dark matter in galaxies with minimal stellar content. Lensing also reveals small-scale clumps within halos. These clumps produce subtle distortions in the images of background galaxies. The presence of these clumps aligns with predictions from dark matter models in which halos contain substructure. The size and distribution of these clumps influence how stars move within galaxies and how satellites orbit. Observations of these small distortions help refine models of dark matter. The bending of light by dark matter also provides information about how mass becomes distributed in regions surrounding galaxies. In many systems, the halo density decreases, gradually forming a smooth transition between the inner region and the outer environment. Lensing measurements help determine the rate at which density declines. These measurements reveal that halos extend to large distances, often much farther than the visible disks. Lensing observations reveal that dark matter dominates the mass of galaxies even in regions with little visible matter. In some galaxies, the lensing signal indicates a large mass component while the stellar content remains low. These systems show that dark matter forms the primary contributor to mass across many environments. The large-scale structure of the universe also becomes revealed through lensing. When surveys map distortions across large regions of the sky, they show how dark matter forms filaments and nodes. These maps allow comparison with simulations of cosmic evolution. The agreement between observed and simulated structures supports the role of dark matter in shaping the universe. The patterns observed in lensing maps reveal how density variations grew over time. These variations match predictions for a universe dominated by dark matter rather than visible matter alone. Without dark matter, the growth would proceed too slowly to match the structures observed today. Lensing also provides information about how dark matter behaves during cluster collisions. When clusters merge, the lensing pattern reveals the location of mass after the collision. In many cases, the lensing signal remains aligned with the galaxies while the gas becomes displaced. This separation provides a clear example of how dark matter behaves differently from visible matter during interactions. Although uncertainties remain about the exact density profiles of halos, the lensing observations provide strong constraints. The mass inferred through lensing often exceeds the amount of visible matter by a large margin. The consistency of this result across many systems supports the presence of dark matter. Lensing also reveals how mass becomes distributed across voids. In some regions, the lensing signal becomes minimal, indicating low mass density. These regions correspond to voids in the cosmic web. The contrast between dense regions and voids reveals how dark matter shapes the distribution of galaxies. In this region, gravitational lensing provides a direct way to trace the presence of dark matter. Its influence becomes visible through the bending of light, revealing structures that cannot be detected through electromagnetic observations alone. The distribution of dark matter inferred from lensing aligns with the behavior observed in galaxy motions, gas temperatures, and cluster collisions. Although the identity of dark matter remains unknown, its gravitational influence forms a consistent pattern across all observations. From this region, the movement inward will continue to the structure of dark matter halos around galaxies, where the unseen mass becomes organized into extended forms that influence the internal dynamics of galaxies. Within the environment shaped by gravitational lensing and the rotation of galaxies, dark matter organizes itself into extended halos that surround galaxies and determine much of their internal behavior. In this region, the focus rests on how these halos form, how they become structured, and how they influence the motion of stars, gas, and satellite systems within and around each galaxy. Although dark matter remains unseen, its distribution becomes inferred through gravitational effects that persist across the full extent of the halo, extending far beyond the visible boundaries of the galaxy. A dark matter halo forms when matter in the early universe collapses under gravity. Because dark matter does not interact with radiation, it does not cool in the same way as visible matter. Instead, it remains in extended regions shaped only by gravitational forces. As the halo grows, it forms a potential well into which visible matter eventually falls. Within this well, gas collapses toward the center, forming stars and eventually creating the visible galaxy. The shape and depth of the halo influence how rapidly stars form, and how the disk or spheroid develops. Observations reveal that halos extend to distances many times larger than the visible region. In the Milky Way, for example, the stellar disk occupies the inner region, while the halo stretches far beyond the farthest stars. The density of dark matter decreases with distance from the center, yet even at large distances, the halo exerts gravitational influence strong enough to shape the motions of satellite galaxies and stellar streams. These motions provide information about the density profile of the halo. Stars in the outer regions of galaxies move at speeds that remain too high for visible matter alone to account for. The presence of the halo provides the necessary mass to bind these stars to the galaxy. The shape of the halo influences the orbits of stars. If the halo becomes elongated, stars move in patterns that reveal the asymmetry. Observations of these orbits help determine whether halos are spherical, elliptical, or flattened. Although no single shape fits all galaxies, many halos appear slightly elongated or triaxial. These shapes reflect the formation history of the halo and the interactions it experienced. Gas within galaxies also reveals the influence of the halo. In many spiral galaxies, gas extends farther than the stars. Its rotation speeds match the predictions for a halo extending beyond the visible region. These speeds decrease only slowly, indicating that the mass of the halo remains significant at large distances. In some galaxies, gas reveals warping or bending in the outer disk. These features arise from interactions between the disk and the halo, indicating that the halo's gravitational influence remains strong even at great distances. Satellite galaxies orbit larger systems within the gravitational environment shaped by the halo. The paths of these satellites provide a way to measure the mass contained in the halo. Their speeds and distances reveal how dark matter becomes distributed. In many systems, satellites orbit at distances where visible matter remains scarce, yet their motions show that the halo continues to dominate. These systems provide information about how far the halo extends. The gravitational influence of the halo also affects how satellites evolve. Satellites passing near the center of the halo experience tidal forces that can stretch or strip them. These tidal interactions produce streams of stars that trace the path of the satellite. The shape and thickness of these streams reveal variations in the density of dark matter along their paths. In some regions, small clumps of dark matter cause disturbances in the streams. These disturbances provide information about the fine structure of the halo. Some observations reveal that halos contain small substructures consistent with predictions from certain dark matter models. These substructures arise naturally when dark matter collapses under gravity. Their presence influences the motion of stars in streams and the orbits of satellites. Although these clumps do not emit light, their gravitational influence becomes visible through small deviations in stellar motions. Simulations predict that halos should contain many such substructures. Observations continue to refine the number and size of these clumps, providing constraints on dark matter models. The interaction between visible matter and the halo influences the formation of galactic disks. The halo stabilizes the disk against certain instabilities. Without the mass of the halo, the disk might develop strong distortions or collapse toward the center. The halo provides a stabilizing influence, allowing the disk to maintain its shape over long periods. Bars within galaxies also reveal the influence of the halo. These elongated structures rotate within the disk, and their speeds depend on the distribution of mass in the halo. A dense halo can slow the rotation of the bar, while a less dense halo allows faster rotation. Observations of bar speeds provide information about the density of the inner halo. Although uncertainties remain, these measurements help refine models of halo structure. In some galaxies, the halo influences the formation of spiral arms. These arms arise from patterns of density waves moving through the disk. The gravitational environment created by the halo affects how these waves propagate. The thickness and stability of spiral arms reveal the influence of the halo. In many spiral galaxies, the presence of dark matter allows the arms to remain stable over long periods. The halo also influences how gas flows within galaxies. Gas falling into the halo becomes heated and slows as it encounters pressure from the surrounding environment. The cooling of gas depends on the depth of the halo. Deeper halos cause gas to heat more before it cools and forms stars. This behavior influences how quickly stars form. In massive halos, star formation may slow because gas cannot cool quickly enough. In smaller halos, gas cools more easily, allowing star formation to proceed more rapidly. The distribution of dark matter also influences how galaxies merge. When two galaxies approach one another, their halos interact first. The halos merge before the visible components do. This interaction shapes the paths of the galaxies as they move toward one another. The resulting merged galaxy inherits the combined halo. The shape and density of this new halo influence how the merged system evolves. Observations of halo structure continue to refine the understanding of dark matter. Although the exact identity of dark matter remains unknown, its distribution within halos remains consistent across many systems. The gravitational influence of the halo shapes the motion of stars, gas, and satellites. These influences appear across galaxies of many types and sizes. Even dwarf galaxies possess halos, although their halos remain less massive. The presence of halos in these small systems reveals that dark matter influences even the smallest structures. The internal behavior of halos continues to be studied. Some models predict that halos should have dense centers, while others predict shallower central regions. Observations show mixed results, with some halos appearing more concentrated than predicted, and others appearing less so. These differences may reflect variations in galaxy formation processes or differences in dark matter properties. In this region, the structure of dark matter halos becomes a central feature of galactic dynamics. Halos shape the motion of stars, the behavior of gas, the orbits of satellites, and the long-term evolution of galaxies. Although uncertainties remain about certain aspects of halo structure, the presence of an extended halo remains well supported. From this region, the movement inward will continue to the environment of the local group, where dark matter influences the motion of galaxies near the Milky Way and shapes the structure of systems within this small cosmic neighborhood. Within the region, inside the larger halos that shape individual galaxies, the environment of the local group reveals how dark matter influences the motion and arrangement of systems on the scale of a few million light-years. In this region, the Milky Way, Andromeda, and several dozen smaller galaxies move within a shared gravitational landscape defined largely by their combined dark matter halos. Although the visible stars and gas within these galaxies provide only a small portion of their total mass, their motions reveal the gravitational pull of a much larger unseen component extending throughout the space between them. The local group contains two dominant galaxies, the Milky Way and Andromeda. Each possesses an extended halo of dark matter that surrounds the visible disk or spheroid. These halos stretch so far that they overlap, shaping the gravitational structure of the entire region. The motions of smaller galaxies within the local group follow paths determined by the combined influence of these large halos. Many of these smaller galaxies orbit either the Milky Way or Andromeda, forming families of satellites bound within the extended gravitational environment. The speeds of these satellites reveal the mass of the halos. Some satellites move at speeds that exceed what would be expected if only visible matter were present. Their motions indicate that dark matter dominates the mass of both major galaxies. The distribution of dark matter within the local group influences how these satellites evolve. Tidal forces from the halos stretch and distort the satellites, sometimes stripping stars that form long streams trailing behind the smaller systems. These streams provide information about the structure of the halos. Their shapes and thicknesses reflect variations in the gravitational potential. Subtle disturbances in the paths of stars within these streams may reveal the presence of small clumps of dark matter within the halo. The presence of these clumps aligns with predictions from dark matter models that include fine-scale structure. The smaller galaxies within the local group also contain dark matter halos of their own. These halos remain much less massive than those surrounding the larger galaxies, yet they influence how the dwarfs evolve. Many dwarf galaxies possess very little visible matter, yet the gravitational pull within them remains stronger than expected. This behavior suggests that dark matter dominates their mass. Their motions within the local group show how dark matter influences systems of many sizes. The environment between galaxies also reveals the influence of dark matter. The space between the Milky Way and Andromeda contains diffuse material, yet the gravitational pull remains determined by the large halos. The two galaxies move toward one another at a speed indicating that their total mass remains larger than the visible content. Their approach reflects the combined gravitational influence of their halos. Although they remain separated by several 100,000 parsecs, their motion reveals the presence of a deep gravitational potential shaped by dark matter. In addition to the two large galaxies, smaller groups within the local group reveal their own structures. These groups contain dwarf galaxies that orbit one another or share common motion. The behavior of these systems indicates that dark matter influences even these smaller environments. Their motions reflect the gravitational pull of halos extending beyond their visible matter. Observations of gas within the local group also reveal the influence of dark matter. Gas between galaxies moves through the combined gravitational environment. Some of this gas becomes heated, while some remains cool. Its behavior depends on the depth of the potential wells created by the halos. In regions where the gravitational potential remains deep gas becomes pulled inward. In regions where the potential remains shallow, gas may drift outward. These flows reveal the distribution of mass. The structure of the local group continues to evolve. Over time, galaxies within the group move along paths influenced by the distribution of dark matter. The Milky Way and Andromeda gradually move closer, guided by their combined halos. Smaller galaxies orbit these large systems, sometimes falling inward and merging with them. These mergers influence the evolution of the halos, causing them to grow larger over time. The interactions between galaxies also influence the distribution of dark matter within the halos. When a satellite approaches the Milky Way or Andromeda, its halo becomes distorted by tidal forces, and some of the dark matter may become stripped. This stripped material mixes with the halos of the larger galaxies. These interactions help shape the distribution of dark matter in the region. The paths of galaxies within the local group also reveal the influence of the surrounding cosmic web. Filaments of dark matter connect the local group to nearby groups and clusters. These filaments influence how matter flows into the region. The alignment of galaxies along these filaments reflects the influence of dark matter structures extending beyond the local group. Observations reveal that galaxies in the local group align along certain directions, reflecting the orientation of these filaments. The local group remains part of a larger structure known as the local sheet, which contains several nearby groups of galaxies. This structure reveals how dark matter shapes environments beyond individual groups. The motions of galaxies within the sheet reflect the gravitational influence of dark matter on larger scales. The distribution of dark matter within the local group aligns with predictions from simulations. These simulations show how groups of galaxies form within the cosmic web, with dark matter halos merging and growing over time. The observed structure and motions of galaxies within the local group match these predictions, supporting the conclusion that dark matter forms the dominant mass component. The fine structure of the dark matter distribution within the local group continues to be refined. Observations of stellar stream satellite motions and halo shapes help determine how mass becomes distributed. Although uncertainties remain regarding certain details, the presence of dark matter in this region remains well supported. The influence of dark matter extends beyond the immediate environment of each galaxy. It shapes how galaxies move within the group, how satellites orbit, and how the group evolves over time. The gravitational effects observed across many systems provide consistent evidence for the presence of an extended distribution of unseen mass. In this region, dark matter appears not as isolated halos, but as a continuous gravitational environment extending across the local group. The dominance of unseen mass shapes the structure and motion of every galaxy within the region. From this region, the movement inward will continue toward the halo surrounding the Milky Way, where detailed measurements reveal the structure of the unseen mass, shaping the environment of our own galaxy. Within the shared gravitational environment of the local group, the halo surrounding the Milky Way reveals how dark matter shapes the structure and behavior of our home galaxy across distances extending far beyond the visible disk. In this region, measurements of stellar motions gas behavior, satellite orbits, and stellar streams provide detailed information about the unseen mass that forms the majority of the Milky Way's total mass. Although the visible galaxy consists of stars, gas, and dust arranged into a thin rotating disk with a central bulge, these components form only a small portion of the mass influencing the motions of objects within the system. The dark matter halo surrounding the Milky Way extends far beyond the outermost stars, forming a diffuse structure that shapes the gravitational environment across hundreds of thousands of parsecs. The presence of this halo becomes evident through the rotation curve of the galaxy. Stars near the Sun move at speeds that exceed what would be expected if only visible matter were present. The rotation curve does not decline at large distances as predicted by classical expectations. Instead, it remains nearly flat. This behavior indicates that much of the mass lies beyond the region occupied by visible matter. The dark matter halo provides the gravitational pull that keeps these stars in stable orbits. Without this unseen mass, many stars would drift outward rather than remain bound to the galaxy. Gas in the outer regions of the Milky Way also reveals the influence of the halo. Radio observations show that neutral hydrogen gas extends farther than the stellar disk. This gas rotates at speeds consistent with the presence of an extended halo. Its behavior confirms that dark matter forms a dominant mass component at distances where the visible galaxy contributes very little. The halo shapes the motion of this gas and influences how it settles into the outer environment. Satellite galaxies orbiting the Milky Way provide additional information about the halo. These satellites include systems such as the Large Magellanic Cloud, the Small Magellanic Cloud, and many smaller dwarf galaxies. Their orbits depend on the mass of the Milky Way's halo. Observations of their speeds and positions reveal that the halo must be massive enough to bind them. In some cases, the velocities of these satellites remain too high to be explained by visible matter alone. This behavior indicates that the halo extends far into the region where satellites orbit. The motions of the Magellanic Clouds reveal particularly strong constraints. These galaxies move at high speeds and follow paths influenced by the halo's gravitational pull. The wake of gas trailing behind them reveals interactions with the halo. These interactions produce structures such as the Magellanic Stream, which extends across the sky. The length and curvature of this stream help determine the shape and density of the halo. The halo also influences the behavior of stellar streams formed from the tidal disruption of smaller galaxies and star clusters. These streams stretch across large distances, tracing paths shaped by the underlying gravitational potential. Variations in the shape of these streams reveal how mass becomes distributed within the halo. In some regions, small perturbations in the streams indicate the presence of dark matter substructures. These substructures produce slight deviations in the motion of stars within the streams. The detection of these perturbations provides evidence for the fine-grained nature of the halo. The density profile of the Milky Way's halo continues to be studied. In the central region, the density appears to increase, while in the outer regions it decreases gradually. The exact shape of this profile remains uncertain yet. Measurements of rotation speeds, satellite orbits, and stellar stream help refine the model. Some observations suggest that the halo may be slightly elongated rather than perfectly spherical. The shape likely reflects the formation history of the galaxy and interactions with surrounding systems. The halo also influences the behavior of the galactic disk. The disk contains stars, gas, and dust arranged into a thin structure that rotates around the center. The halo stabilizes this disk, preventing it from warping excessively. Although some warping occurs in the outer regions, the presence of the halo prevents large distortions. The stability of the disk depends on the mass distribution within the halo. Bar structures within the Milky Way also reveal the influence of the halo. The central bar rotates within the gravitational potential shaped by both visible matter and the halo. The pattern speed of the bar depends on the density of the inner halo. Measurements of this speed help determine how mass becomes distributed near the center. Although the bar influences the motion of stars in the inner region, the halo influences the long-term evolution of the bar. Gas flowing through the Milky Way interacts with the halo as it moves. Inflows of gas from the cosmic web pass through the halo before reaching the disk. The halo influences the temperature and ionization state of this gas. As gas enters the halo, it heats due to interactions with the surrounding environment. The cooling of this gas determines how quickly it can settle into the disk and form new stars. The distribution of dark matter within the halo shapes these processes. The presence of the halo also influences how the Milky Way interacts with nearby galaxies. As Andromeda approaches the Milky Way, their halos influence one another. The gravitational pull between the halos determines the speed and direction of their future collision. As the halos merge, the resulting structure will reflect the combined mass of the two systems. Smaller galaxies also interact with the halo. When a satellite passes through the halo, tidal forces strip stars from the outer regions. These stars form streams that stretch behind the satellite. The shape of these streams reveals the influence of the halo. In some cases, the halo may capture material from the satellite, adding to its mass. The halo also influences the behavior of dark matter itself. Although dark matter does not interact electromagnetically, it interacts gravitationally with other dark matter particles. These interactions shape the distribution of mass within the halo. Over time, the halo becomes more extended as material moves outward. The internal density changes gradually as the halo evolves. Observations reveal that the halo contains substructures predicted by certain models. These substructures arise from the collapse of dark matter in the early universe. Their presence influences how stars move within the galaxy. Although these substructures remain invisible, their gravitational influence can be detected through careful measurements. The Milky Way's halo provides a detailed example of how dark matter shapes galaxies. Although uncertain certainties remain about the precise identity of dark matter, its distribution within the halo remains consistent with well-established models. The gravitational influence of the halo shapes the motion of stars, gas, and satellites. These influences appear across many observations, supporting the presence of a large unseen mass component. In this region, the focus remains on the structure and influence of the Milky Way's dark matter halo. The halo forms the gravitational foundation of the galaxy, shaping its evolution and behavior. From this region, the movement inward will continue to the paths of stellar streams, where fine details in their motions reveal the subtle influence of dark matter on small scales. Inside the gravitational environment shaped by the Milky Way's extended dark matter halo, the paths of stellar streams reveal subtle variations in the unseen mass that surrounds the galaxy. In this region, long ribbons of stars stretching across the halo act as sensitive tracers of the gravitational potential. These streams form when smaller galaxies or star clusters move close to the Milky Way and become gradually pulled apart by tidal forces. As stars drift away from their parent system, they follow orbits shaped by the distribution of mass throughout the halo. Because these streams remain narrow and coherent, even small perturbations in the gravitational field can alter their shape, width, or direction. These alterations provide a detailed map of the invisible environment. When a satellite galaxy or star cluster approaches the Milky Way, tidal forces from the halo remove stars from its outer regions. These stars move ahead or trail behind the satellite, forming structures that stretch across large distances. The stars in these streams follow paths that reveal the shape of the gravitational potential. If the halo were perfectly smooth and spherical, the streams would follow regular arcs. Instead, many streams show slight deviations, suggesting that the halo contains substructures or variations in density. These variations reflect the fine-grained nature of dark matter. Observations of these streams help determine how mass becomes distributed within the halo. Some streams appear slightly thicker or more diffuse in regions where the gravitational field varies. Others show small bends or breaks where the stream encounters a denser region of dark matter. These features provide information about the size and location of unseen clumps. Simulations predict that dark matter halos should contain many small substructures formed as the halo grew over time. These substructures arise naturally when dark matter collapses under gravity. The presence of these clumps influences the motion of stars within the streams. Even a small clump can cause a slight deflection in the path of the stream. These deflections remain visible long after the encounter, providing a record of the distribution of dark matter. Some streams, such as those originating from disrupted globular clusters, show gaps or shifts in their density. These features may arise from interactions with dark matter substructures. Observations of these features help test models of dark matter. If dark matter contains many small clumps, the distribution of these clumps should leave a specific pattern of disturbances in the streams. If dark matter contains fewer clumps or smoother distributions, the pattern would differ. Although uncertainties remain, the observed variations in streams appear consistent with the presence of substructure. Stellar streams also reveal the shape of the global halo. The curvature of a stream depends on the shape of the gravitational potential. If the halo becomes elongated or flattened, the stream will trace this shape. Observations of multiple streams allow researchers to determine the three-dimensional structure of the halo. In the Milky Way, streams suggest that the halo may be slightly elongated rather than perfectly spherical. Although the exact degree of elongation remains uncertain, streams provide strong constraints. Streams also reveal how the halo evolves over time. As the Milky Way grows through interactions with satellites, the distribution of dark matter changes. These changes alter the gravitational potential, influencing the paths of streams. By comparing the observed positions of streams with models of past interactions, researchers can reconstruct how the halo evolved. Although the details of this evolution remain subject to uncertainties, streams provide one of the most sensitive measures of the halo's history. The motion of stars within streams reveals additional information. Some stars move slightly faster or slower than expected, reflecting the influence of the halo's mass. These variations provide information about how dense the halo is in different regions. In some cases, the density appears lower or higher than predicted, suggesting that the halo contains variations that remain unresolved. These variations could arise from dark matter substructures or from interactions with other galaxies. Stellar streams also interact with the disk of the Milky Way. As a stream passes through the disk, the gravitational influence of stars and gas may slightly alter its path. These interactions provide information about the mass distribution within the disk. They also help distinguish between perturbations caused by dark matter and those caused by visible matter. The interplay between the disk and the halo shapes the evolution of streams. Some streams show complex behavior where they pass through regions containing both disk and halo components. Observations of these interactions help refine the understanding of how mass becomes distributed in both components. Although some details remain uncertain, streams consistently reveal the influence of dark matter. The presence of substructures appears necessary to explain certain features. The shape of the halo appears slightly elongated or triaxial. The density profile appears consistent with expectations for a dark matter halo. Although alternative explanations must match all these observations, none so far align as consistently as the presence of dark matter. Streams also reveal how the Milky Way interacts with nearby galaxies. Some streams may originate from dwarf galaxies that passed close to the Milky Way. Their paths reveal how these galaxies move through the halo. These movements provide information about the gravitational environment at the time of their disruption. The presence of streams across the halo indicates that the Milky Way has interacted with many smaller systems over time. These interactions reveal how the halo grew through mergers and accretion. The distribution of streams across the sky reveals the complex history of these interactions. Some streams extend across large distances, while others remain shorter. These differences reflect the mass and orbit of the parent system. Streams that originate from more massive systems may remain broader or contain more stars. Streams that originate from smaller systems may remain narrower. These patterns reveal how the halo influences the evolution of these systems. The presence of streams also influences the long-term evolution of the halo. As stars move along these paths, they contribute to the overall distribution of matter. Although their mass remains small compared to the halo, their distribution helps refine the gravitational potential. Over time, the halo becomes more uniform as streams disperse. Although the identity of dark matter remains unknown, its influence on stellar streams remains evident. The presence of substructures, the shape of the halo, and the evolution of the gravitational potential all align with expectations for a dark matter halo influenced by gravitational interactions. In this region, stellar streams provide a detailed map of the unseen mass surrounding the Milky Way. Their paths reveal the fine structure of the halo, showing how dark matter influences the motion of stars on small scales. From this region, the movement inward will continue to the smaller clumps and substructures predicted by dark matter models, where the focus will shift to the fine-scale behavior of the unseen mass within galaxies. Inside the region mapped by stellar streams, the structure of dark matter becomes finer still, forming small clumps and subhalos predicted by models of how matter collapsed in the early universe. In this region, the focus rests on these substructures which arise naturally when dark matter gathers under gravity, without the cooling processes that shape visible matter. Although these clumps do not emit light and remain difficult to detect directly, their gravitational influence appears subtly in the motions of stars in the paths of stellar streams, and in the distribution of satellite galaxies orbiting larger systems. These small structures form the next inward layer of dark matter's arrangement, revealing how the unseen mass becomes organized at fine scales within galaxies. Subhalos represents smaller concentrations of dark matter orbiting within larger halos. They form early in cosmic history as density variations grow under gravity. As the universe expands, these small halos merge with larger ones, yet many survive as distinct structures. Within a galaxy such as the Milky Way subholos move along paths shaped by the host halo's gravitational potential. Their sizes range from systems large enough to host dwarf galaxies to structures too small to contain visible matter. Their presence influences the motion of surrounding stars subtly but measurably. Simulations of cosmic structure formation predict that halos like the Milky Way should contain many subhalos. These predictions arise because dark matter collapses first into small structures before merging into larger ones. The smallest predicted halos may remain too small to be detected directly through observations of stars or gas. However, their gravitational influence can appear indirectly. These subhalos influence stellar streams by causing small deflections or gaps along the stream's path. Observations of several streams reveal features that may arise from interactions with subhalos. Although some disturbances may result from interactions with visible matter components, others appear consistent with the influence of unseen clumps. These features provide clues about the number and size of subhalos within the halo. The spatial distribution of subhalos also influences how satellite galaxies evolve. Dwarf galaxies orbiting the Milky Way may experience tidal forces from both the main halo and the subhalo within it. These forces can strip stars from the satellites or alter their orbits slightly. Observations of these effects help determine the number of subhalos and their distribution. Some satellite galaxies appear to reside within larger subhalos that provide additional gravitational support. This behavior influences how these galaxies form and evolve within the halo. Subhalos also influence the distribution of gas within galaxies. As gas moves through the halo, the gravitational influence of subhalos can alter its path. These interactions may produce small disturbances in the distribution of gas in the outer regions of galaxies. Although these disturbances remain subtle, they provide additional clues about the presence of subhalos. The density profile of subhalos remains a subject of ongoing study. Some models predict dense central regions, while others predict shallower profiles. The behavior of dark matter near the centers of these subhalos influences their gravitational impact. Observations of stellar streams provide constraints on these profiles. If subhalos contain dense cores, their interactions with streams produce sharper features. If their profiles remain shallower, the features may appear more diffuse. Although uncertainties remain, observations help refine these predictions. Subhalos also influence the long-term evolution of galaxies. As they move through the halo, they exchange energy with the surrounding matter. This process gradually alters their orbits. Some subhalos may be drawn toward the center of the halo, while others may move outward. These movements influence how the halo evolves. Over time, the distribution of subhalos becomes shaped by the gravitational environment. The presence of subhalos within the halo also influences the distribution of stars in the outer regions of galaxies. As stars move through the halo, interactions with subhalos may alter their orbits. These interactions produce small variations in the density of stars in the outer halo. Observations of these variations provide clues about the number and mass of subhalos. Although the presence of subhalos remains well supported by theoretical predictions, direct detection remains challenging. The smallest subhalos contain no visible matter, making them detectable only through their gravitational influence. The combination of stellar stream disturbances, satellite galaxy motions, and gas behavior provides indirect evidence for these structures. Although uncertainties remain about the number and density of subhalos, the presence of fine-grained structure remains consistent with predictions from dark matter models. The behavior of subhalos in other galaxies also provides insight. Observations of lensing in distant galaxies reveal small distortions that may arise from substructure. These distortions appear as slight deviations in the shapes of background galaxies. Although the signal remains subtle, it provides independent evidence for subhalos. The presence of subhalos influences how galaxies form and evolve within the cosmic web. As matter flows along filaments, subhalos merge to form larger halos. Some subhalos survive the merging process, becoming satellites within the larger halos. These structures influence the distribution of matter within galaxies. Their presence provides a record of the formation history of the galaxy. The number of subhalos within a galaxy provides information about the nature of dark matter. If dark matter behaves as predicted by certain models, the number of small halos should remain large. If dark matter behaves differently, the number may be smaller. Observations of stellar streams and satellite galaxies help refine these predictions. The presence of many small subhalos supports models in which dark matter interacts only through gravity and possibly weak interactions. The fine-scale structure of dark matter remains a key area of study. Although observations continue to refine the understanding of subhalos, the overall picture remains consistent with the predictions of hierarchical structure formation. In this region, the behavior of dark matter reveals itself through subtle gravitational effects. These effects appear across many observations, supporting the presence of substructure within the halo. The influence of these subhalos shapes the motion of stars, the paths of stellar streams, and the evolution of satellite galaxies. From this region, the movement inward will continue to candidate particle properties, where the focus shifts to the physical possibilities for the nature of dark matter itself, based on the constraints provided by the gravitational behavior observed across cosmic environments. Inside the region shaped by the fine structure of subhalos, the focus narrows to the physical possibilities for the particles that may form dark matter. In this region, the unseen mass becomes studied not through its gravitational influence alone, but through the constraints imposed by well-established observations across galaxies, clusters, and the cosmic web. Although the identity of dark matter remains unknown, several properties become strongly supported by evidence. These properties limit the range of possible candidates while leaving multiple possibilities consistent with what is known. The behavior of dark matter across cosmic structures indicates that it interacts very weakly with visible matter. It does not emit or absorb light. It does not scatter photons. It influences its surroundings primarily through gravity. These behaviors suggest that dark matter must be electrically neutral and must not participate in electromagnetic interactions. The absence of strong or electromagnetic interactions explains why dark matter does not form bright structures or lose energy through radiation. Because dark matter does not cool through radiation, it remains in extended halos, rather than collapsing into dense disks or stars. The ability of dark matter to pass through collisions, as observed in cluster interactions, places further constraints on its properties. The material does not slow significantly during these collisions, indicating that dark matter does not experience strong interactions with itself. If dark matter particles interacted strongly, their halos might show signs of scattering or compression. Instead, the halos pass through one another with minimal disruption. This behavior suggests that dark matter interactions remain weak. Dark matter must also possess enough mass to influence the formation of structures across large scales. If dark matter were massless, it would behave like radiation and would not form the deep gravitational wells required to explain cluster dynamics. At the same time, the particles must not be too heavy. If they were extremely massive, they would cluster too strongly on small scales, contradicting the smooth distribution observed in some environments. Observations of the cosmic microwave background and the large-scale structure of the universe provide strong constraints on the mass range of possible particles. These constraints eliminate some possibilities while leaving others viable. Some candidate particles arise from extensions of known theories. One possibility involves weakly interacting massive particles which behave as stable particles with masses large enough to influence cosmic structure, but interactions too weak to be detected through electromagnetic processes. These particles arise naturally in some models of particle physics. Although no direct detections have been confirmed, their properties align with the gravitational behavior observed. Another possibility involves lighter particles that behave as extremely weakly interacting fields. These particles could behave similarly to waves on large scales, influencing the distribution of matter smoothly across cosmic structures. Their interactions would be extremely subtle, making them difficult to detect directly. Although uncertainties remain, such fields remain consistent with observations. Some observations of small-scale structures place additional constraints. The presence of many subhalos supports models containing cold dark matter, meaning that the particles moved slowly during the early universe and allowed small structures to form. If dark matter were warm or hot moving at high speeds in early times, it would erase small-scale structures. Observations of stellar streams and dwarf galaxies support the presence of small-scale structure consistent with the idea that dark matter particles moved slowly during formation. The need for dark matter to form halos of many sizes further constrains its properties. The fact that dwarf galaxies remain dominated by dark matter, while larger galaxies contain more visible matter, reveals how dark matter behaves across environments. The consistency of these behaviors supports models in which dark matter particles remain stable over long periods. If dark matter decayed rapidly, its gravitational influence would change over time. Instead, observations reveal structures that match long-term stability. Observations of collisions between clusters also constrain the interactions and strength between dark matter particles. If these particles scattered frequently, the dark matter halos would slow during the collision. Instead, the halos pass through with little disruption. This behavior suggests that dark matter interacts less strongly than particles influenced by the strong nuclear force. The lack of interaction with the electromagnetic radiation also supports this conclusion. Some particle candidates arise from theoretical frameworks exploring new symmetries in physics. These frameworks propose that dark matter might consist of particles that interact through a new force that remains much weaker than the forces affecting visible matter. Although such forces remain hypothetical, they remain consistent with observations if they produce interactions too weak to detect directly. Candidate particles must also remain consistent with the cosmic microwave background. The patterns in the background radiation reveal how matter became distributed during the early universe. These patterns reflect the influence of dark matter. The observed structure supports models in which dark matter does not interact with radiation after the early stages. This behavior reflects the need for dark matter to behave as a stable neutral component. Some constraints arise from observations of gravitational lensing. The distribution of dark matter inferred from lensing must match the predictions of models involving candidate particles. The presence of small clumps within halos supports models of cold dark matter rather than warm or hot dark matter. The smooth distribution across large scales must also match these predictions. These constraints limit the range of possible particle masses. The presence of extensive substructure supports models in which dark matter behaves as a cold collisionless component. Some thermal properties of dark matter can be inferred from its influence on the distribution of matter. If dark matter particles possess significant thermal motion at early times, the smallest structures predicted by simulations would not form. Because such structures appear to exist, these particles must have moved slowly enough to allow them to develop. The stability of dark matter across billions of years also constrains the possible interactions. If dark matter particles decayed into lighter particles, the distribution of mass would change over time. Observations reveal that dark matter halos remain stable across cosmic history, indicating that dark matter remains long-lived. The gravitational influence of dark matter must also remain consistent with general relativity. Observations of gravitational lensing. Galaxy rotation curves and cosmic structure align with the predictions of general relativity when dark matter becomes included. Although alternative theories of gravity have been proposed, they must match all observations across many environments. Some alternative theories can explain certain behaviors but fail to match others. The consistency of dark matter across many observations supports its presence as a real component rather than a modification of gravity alone. Although the identity of dark matter remains uncertain, the properties supported by observations provide a clear description. Dark matter must be electrically neutral, weakly interacting, stable and massive enough to influence structure formation. The particles must behave as collisionless matter across most environments, allowing halos to persist without disruption during collisions. These constraints limit the range of possible candidates, but leave several possibilities open. In this region, the focus remains on the physical properties of dark matter that align with observations. Although many theoretical possibilities exist, the behaviors supported by evidence constrain the options. The gravitational influence of dark matter across galaxies, clusters, and the cosmic web provide strong limits on how these particles must behave. From this region, the movement inward will continue to the methods used to search for dark matter, where the focus shifts to the experiments, observations, and detectors designed to identify interactions that might reveal the nature of the unseen mass. Inside the region shaped by the physical constraints on dark matter, the focus moves to the methods used to search for direct or indirect evidence of these particles. In this region, dark matter becomes studied through experiments and observations designed to detect its extremely weak interactions with visible matter or its influence on radiation and particle behavior. Although no confirmed detection has been made, the search continues across many approaches, each informed by the gravitational evidence accumulated across galaxies, clusters, and the cosmic web. One approach involves looking for rare collisions between dark matter particles and atoms. Because dark matter does not interact through electromagnetic forces, these collisions would be extremely weak. Experiments designed to detect such interactions use very sensitive detectors placed deep underground to shield them from background radiation. These detectors contain materials that might respond when a dark matter particle transfers a small amount of energy to an atomic nucleus. The response might appear as a tiny flash of light or a small vibration in the detector. Although several experiments have reported signals that require further investigation, none have provided a confirmed detection. These experimental efforts remain motivated by theoretical models predicting that dark matter should occasionally interact through weak forces. Another approach involves searching for signals from dark matter particles interacting with one another. If dark matter particles can collide and produce radiation, this radiation might become detectable in regions where dark matter density remains high. The centers of galaxies, clusters, or dwarf galaxies may contain dense regions where these interactions occur more frequently. Telescopes observing gamma rays, X-rays, or radio waves search for patterns that might indicate such interactions. Although some observations have shown unusual signals, no clear evidence exists that these signals arise from dark matter. Uncertainties in astrophysical processes make it difficult to attribute these signals to unseen particles. A third approach involves producing dark matter particles in particle accelerators. Machines that accelerate particles to high energies create conditions similar to those present during the early universe. Under certain conditions, these collisions could produce dark matter particles. Because dark matter does not interact electromagnetically, these particles would not appear directly in detectors. Instead, their presence would become inferred through missing energy or missing momentum in the collision. Experiments at particle accelerators continue to search for such signatures. Although no confirmed detections have been made, the constraints from these searches help narrow the range of possible particle masses and interaction strengths. Observations of the universe also provide indirect methods for detecting dark matter. Some models predict that dark matter might interact weakly enough to produce radiation detectable through telescopes. Observations of dwarf galaxies and the center of the Milky Way provide opportunities to search for such signals. These regions contain high concentrations of dark matter, making them ideal environments for indirect searches. Although some observations have shown anomalies, none have been confirmed as dark matter signatures. The search for dark matter also includes efforts to detect the influence of dark matter particles on cosmic radiation. Some models predict that dark matter may influence the cosmic microwave background through its interactions with other particles during the early universe. Observations of this radiation reveal patterns that provide constraints on the possible properties of dark matter. These patterns align with models in which dark matter behaves as a neutral weakly interacting component. Any alternative model must match these observations. Some experiments search for very light dark matter particles, which might behave more like waves than particles on large scales. These particles could influence electromagnetic fields in subtle ways. Experiments use resonant cavities or sensitive electromagnetic detectors to look for small effects that might arise from these interactions. Although no confirmed detections have been made, these experiments continue to refine the limits on possible particle properties. Efforts to detect dark matter include searching for its influence on atomic behavior. Some models predict that dark matter might cause small changes in the energy levels of atoms. Experiments that measure atomic transitions with high precision might detect such changes. Although no confirmed signals exist, high-precision measurements provide further constraints. Some attempts to detect dark matter explore the influence of dark matter particles on the behavior of gravitational waves. Although dark matter does not interact with gravitational waves, its presence influences the distribution of mass in regions where these waves travel. Observations of gravitational wave events provide information about the distribution of mass and might reveal small deviations caused by dark matter. Although these effects remain subtle, future observations may refine these constraints. Searches for dark matter also examine how dark matter particles might interact with neutrinos. Although neutrinos interact weakly with matter, dark matter might influence their behavior. Experiments detecting neutrinos could reveal subtle signals consistent with dark matter. Although no such signals have been confirmed, the possibility remains subject to ongoing research. Despite the lack of direct detection, the search for dark matter remains guided by gravitational evidence. The behavior of galaxies clusters and the cosmic web reveals that dark matter must exist as a stable component. The constant search for direct detection aims to identify the physical nature of this component. Experiments use a wide range of materials and techniques to detect interactions with dark matter particles. Some use noble gases cooled to low temperatures. Others use crystals that produce light when particles strike them. Others use superconducting materials sensitive to small vibrations. Each method aims to reveal the tiny energy transfers expected if dark matter collides with atoms. Some searches focus on detecting dark matter that moves faster or slower than expected. These experiments refine the range of possible particle speeds. Although dark matter moves slowly on cosmic scales, its speed distribution within the Milky Way halo might produce detectable differences. The distribution of dark matter in the halo also influences the expected rate of collisions. Experiments account for these differences by conducting observations over long periods. Some experiments search for annual variations in detection rates which might arise as the Earth moves through the halo. Although subtle variations have been reported, they remain unconfirmed. Other experiments search for dark matter using detectors placed in space. These detectors look for particles or radiation that might indicate dark matter interactions. Although such observations face challenges from background radiation, they provide data from environments outside the Earth's atmosphere. Large-scale telescopes also contribute to the search. Observations of galaxy clusters, Gravitational lensing and cosmic structure provide constraints on dark matter models. These observations do not detect dark matter directly, but refine the range of possible properties. Although the identity of dark matter remains unknown, the search continues with increasing sensitivity. Each experiment, whether successful or not, provides information that narrows the possibilities. The lack of detection in certain ranges eliminates some candidates, helping refine the focus on others. The combination of experimental and observational approaches forms a consistent effort to reveal the physical nature of dark matter. In this region, the focus remains on the methods and observations used to search for dark matter. These efforts provide constraints that shape the understanding of possible particle properties. Although uncertainties remain, the search continues guided by gravitational evidence. From this region, the movement inward will proceed toward the open questions and boundaries where the remaining uncertainties become described without speculation, marking the inner region of what is known and what remains unresolved. Inside the region defined by search methods and physical constraints, the movement reaches the boundary between what is well established about dark matter and what remains uncertain. In this region, the scientific understanding retains clarity regarding the gravitational role of dark matter, while acknowledging areas where evidence remains incomplete. These uncertainties do not replace what is known. Instead, they outline the limits of current knowledge and define the questions that continue guiding research. The existence of dark matter becomes supported by many independent observations. The motions of galaxies within clusters require additional mass. The rotation curves of galaxies remain too flat to be explained by visible matter alone. The patterns in the cosmic microwave background reveal density variations influenced by a dominant unseen component. The formation of large-scale structures requires a mass component that does not interact strongly with radiation. Gravitational lensing reveals mass in regions lacking visible matter. Cluster collisions show that the mass moves ahead of the gas rather than slowing. These lines of evidence collectively support the presence of a stable neutral component that interacts primarily through gravity. Although this gravitational evidence remains strong, the identity of dark matter remains uncertain. Direct detection experiments have yet to observe interactions between dark matter particles and visible matter. Experiments sensitive to weak interactions have not confirmed a particle responsible for the unseen mass. The absence of detection in certain mass ranges eliminates some possibilities, but does not reveal the nature of dark matter. Searches for dark matter particles produced in accelerators have not confirmed missing energy signatures consistent with dark matter. Although constraints from these experiments narrow the range of possible particle properties, they do not provide a confirmed identity. Observations. Searching for radiation arising from dark matter interactions have also not produced confirmed detections. Unusual signals observed in some regions remain subject to astrophysical uncertainties. These observations do not confirm or dismiss the presence of dark matter, but illustrate the complexity of interpreting signals from dense environments. Alternative explanations for certain observations remain possible but must match all known behavior. Some alternative theories propose modifying the laws of gravity. These theories can reproduce certain observations, such as the behavior of galaxy rotation curves. However, many struggle to match the full range of evidence across scales. They often fail to reproduce the structure of clusters, the behavior of the cosmic microwave background, or the distribution of mass revealed through gravitational lensing. Although these theories remain studied, they have not replaced the model in which dark matter exists as a real component. Uncertainties also remain regarding the fine-scale structure of dark matter. Although models predict many small subhalos, The exact number and distribution remain uncertain. Observations of stellar streams reveal some substructure, yet limitations in data quality and coverage mean that the smallest subhallus remain difficult to detect. Some differences between observations and simulations may reflect uncertainties in how visible matter influences the evolution of subhalos. The density profiles of dark matter halos remain subject to ongoing study. Some observations suggest that the inner regions of halos remain less dense than predicted by certain models. These differences may arise from the influence of visible matter on the halo, or may reflect limitations in those models. The interaction between dark matter and visible matter near the centers of galaxies remains complex and continues to be refined. Uncertainties also surround the distribution of dark matter in the central regions of clusters. Although lensing reveals mass concentrations, the precise shape of the distribution remains difficult to measure. Gas interactions, galaxy motions, and gravitational influences interact in complex ways that require careful interpretation. The stability of dark matter over cosmic time remains well supported, yet the possibility that dark matter might possess small interactions beyond gravity remains under study. These interactions, if present, must be extremely weak to match observations. Although some models predict such interactions, no confirmed evidence exists. The role of dark matter in the early universe also contains uncertainties. Although the influence of dark matter on the cosmic microwave background provides strong constraints, the behavior of dark matter during the earliest moments remains less certain. The separation between dark matter and radiation, the formation of the first halos, and the influence of dark matter on early star formation remain topics of active research. The composition of dark matter also remains unknown. It may consist of a single type of particle or a combination of components. Observations remain consistent with a dominant component that behaves as cold dark matter. The presence of additional components remains possible but must remain consistent with observations. These uncertainties highlight the limits of what is known, but do not contradict the gravitational evidence supporting the presence of dark matter. They form the inner boundary of current understanding where open questions remain, yet remain framed by established facts. The interplay between theory and observation continues to refine this boundary. Future measurements may resolve some uncertainties, yet others may persist as observational limits remain. The gravitational influence of dark matter remains consistent across many environments, yet the fine-scale behavior, particle identity, and detailed interactions remain subjects of continuing research. Although many search methods remain sensitive to potential signals, the lack of detection thus far keeps the particle identity unresolved. The region also includes uncertainties about how dark matter interacts with visible matter on the smallest scales. Some observations suggest variations in how dark matter influences the inner regions of galaxies. These variations may reflect differences in baryonic processes such as star formation and gas dynamics, or may indicate differences in the distribution of dark matter. Distinguishing between these possibilities remains an active area of research. The role of dark matter in the formation of dwarf galaxies remains another open question. Some dwarf galaxies appear missing in observations relative to predictions. This difference may reflect observational limitations, or may reflect differences in how dark matter influences small systems. The interplay between dark matter and visible matter in these galaxies remains complex and continues to be refined. The behavior of dark matter during cluster collisions remains well supported on large scales. However, small uncertainties remain about how dark matter behaves in certain environments. Some collisions show subtle differences in the separation between gas and dark matter. These differences may reflect variations in cluster structure, or may indicate complexities in dark matter behavior. The gravitational lensing of distant galaxies reveals mass distributions consistent with dark matter. However, the interpretation of lensing signals remains challenging in regions with complex structures. Observational uncertainties may influence the inferred distribution of mass. These uncertainties do not undermine the presence of dark matter, but highlight the challenges of interpreting signals in complex environments. Although dark matter remains required to explain the observed universe, the precise nature of the unseen mass remains unresolved. These uncertainties form the inner boundary of scientific understanding. They define what remains unknown without extending beyond established evidence. These open questions guide future research and help refine the understanding of dark matter. In this region, the gravitational role of dark matter remains established, while the identity of the material remains undetermined. The limitations of experiments and observations define the boundary of current knowledge. From this region, the movement inward will reach the final conceptual layer, where the well-supported scientific picture of dark matter becomes described without summarizing or interpreting meaning, forming the inner core of what is known today. Inside the boundary marked by open questions and observational limits, the movement arrives at the innermost region where the present scientific consensus on dark matter forms the central well-supported structure of understanding. In this region, the description rests solely on what evidence consistently supports across scales, ranging from individual galaxies to the full distribution of matter throughout the observable universe. This core picture does not explain the identity of dark matter, nor does it resolve uncertainties about the smallest structures or particle properties. Instead, it describes the stable framework that remains unchanged by ongoing refinements and forms the foundation upon which all further study continues. The consensus rests first on gravitational evidence that remains consistent across independent methods. Galaxy rotation speeds reveal that visible matter accounts for only a fraction of the mass required to bind stars to their orbits. These rotation curves remain flat across distances where the visible disk contributes little mass. The additional mass required to explain these motions becomes attributed to dark matter distributed in an extended halo. This behavior appears across galaxies of many types and sizes, establishing that the presence of unseen mass forms a general feature of galactic structure rather than an anomaly. In galaxy clusters, the motions of galaxies require more mass than visible matter can provide. The temperature of hot gas trapped within clusters also requires a deep gravitational well. Gravitational lensing reveals mass in regions where little visible matter exists. These independent lines of evidence collectively support the presence of dark matter as the dominant mass component in clusters. Although the distribution of mass in certain clusters contains uncertainties due to complex interactions, the overall gravitational influence remains well supported. The large-scale structure of the universe also requires dark matter. The formation of filaments, walls, and voids arises naturally when dark matter acts as a gravitational scaffold guiding the flow of gas and the formation of galaxies. Without dark matter, the observed structures could not form within the available time. Simulations that include dark matter reproduce the distribution of galaxies across billions of light years. These results align with observations of the cosmic web, supporting the role of dark matter in forming large-scale structures. The cosmic microwave background provides another line of evidence. The patterns in the temperature and polarization of this radiation reveal density variations present when the universe was young. These variations require the presence of a non-radiating mass component capable of influencing gravity without interacting strongly with radiation. The distribution of peaks and troughs in the background matches models containing dark matter. This consistency supports the presence of a stable neutral component throughout cosmic history. Gravitational lensing provides further confirmation. The bending of light from distant sources reveals mass distributions that do not align with visible matter alone. Both strong and weak lensing produce maps of mass in regions where no stars or gas reside. These maps reveal halos around galaxies, clusters, and large-scale structures, reinforcing the conclusion that dark matter forms a significant part of the mass in these environments. The behavior of colliding clusters also supports this picture. In some collisions, the gas slows due to interactions while the inferred mass moves ahead. This separation between visible matter and gravitational influence reveals that the unseen mass does not experience strong interactions with gas or visible matter. Instead, it passes through the collision largely unaffected. This behavior supports models in which dark matter interacts extremely weakly with itself and with visible matter. The consensus also includes the understanding that dark matter forms halos with density profiles decreasing outward. Although details of these profiles vary between systems, the presence of extended halos remains consistent. Observations of satellite galaxies, stellar streams, and gas behavior reveal that halos extend far beyond visible regions. These halos influence the motions of stars and satellites and shape the stability of galactic disks. In many galaxies, the halo provides the majority of the mass, influencing their dynamics. The presence of small-scale structures within halos remains supported by simulations and several observational hints. Although the exact number and mass of these substructures remain uncertain, the presence of some level of substructure appears consistent with data. These structures influence stellar streams and satellite galaxies, providing clues about the internal arrangement of dark matter within halos. The consensus also holds that dark matter must be composed of particles or fields that remain stable over long periods. The gravitational influence of dark matter appears consistent across cosmic time, indicating that dark matter does not decay rapidly. The stability of dark matter forms part of the core picture, supported by the persistence of halos and the distribution of matter across the cosmic web. The lack of electromagnetic interaction remains another key element. Dark matter does not emit or absorb light. It does not scatter photons. Its presence becomes inferred solely through gravity. This behavior explains why dark matter does not form bright structures or collapse into dense disks. The absence of electromagnetic interaction also aligns with observations of cluster collisions where dark matter does not slow as gas does. The consensus includes constraints on possible interactions beyond gravity. Any additional interactions must remain extremely weak to match observations. The behavior of dark matter during cluster collisions reveals that self-interactions must be minimal. Observations of the cosmic microwave background and large-scale structure also support models in which dark matter interacts weakly, allowing structure to form in a way consistent with the observed universe. Although experiments continue to search for dark matter particles, the lack of detection does not contradict the consensus. It reflects the expectation that dark matter interacts weakly. Each null result refines the allowed range of particle masses and interaction strengths without altering the established gravitational picture. The consensus remains broad and not dependent on a specific particle model. It describes dark matter as a stable non-luminous component that interacts primarily through gravity, forms extended halos around galaxies, influences the formation of large-scale structures, and shapes the distribution of matter throughout cosmic time. Although uncertainties remain within this framework, the core elements appear robust across observations. The innermost region of understanding contains no speculation about meaning or purpose. It describes only the stable structure supported by evidence. Dark matter forms a dominant component of the universe's mass. Its gravitational influence shapes galaxies, clusters, and the cosmic web. Its identity remains unknown, yet its presence remains supported by many independent lines of evidence. This core picture remains unchanged as research continues. The movement inward now reaches completion. From this central region, the transition will proceed toward the wind down, where the pace will slow and the narration will soften, guiding the listeners gently from the scientific center toward rest. In the quiet inner region of the topic, the understanding of dark matter rests in a steady, stable place shaped by the weight of evidence gathered across many scales. The outward layers of galaxies, clusters, and the cosmic web remain shaped by its gravity, and the inner regions of halos, substructures, and particle constraints form a consistent picture of a calm, unseen presence that guides the structure of the universe. Here the narration eases into a slower rhythm, allowing the mind to settle as the ideas drift toward the stillness. The universe stretches across distances that reach far beyond the limits of sight, yet the behavior of matter within it follows patterns shaped by something quiet and unlit. Stars move along paths held in place by deep wells of unseen mass. Galaxies gather into clusters and drift through filaments. Light bends gently around regions where no visible structures reside. These motions form a calm pattern, steady across time, revealing an ordered environment shaped by a component that remains constant. Although the identity of this unseen material remains unknown, its presence brings cohesion to the structures filling space. In many galaxies, extended halos maintain the motion of stars in the outer regions. In clusters, the gravitational pull of a dark matter binds galaxies within vast volumes. Across the cosmic web, dark matter forms the framework guiding the flow of gas and the formation of stars. These features remain consistent and form the quiet structure of the universe. As the narration moves inward, the focus stays on the calm steadiness of these patterns. The unseen mass shapes the space around it without radiating or scattering light. It does not rush or collide strongly, but passes through interactions without disruption. Its behavior remains constant across billions of years, providing continuity within the changing universe. This stability allows stars to orbit galaxies, to form and large-scale structures to develop. In the quiet inner environment of this understanding, the unknown identity of dark matter rests without urgency. The questions about its nature remain open, yet do not disturb the stable picture supported by observation. The gravitational influence of dark matter continues to guide the structure of space, whether the particle remains revealed or not. This calm acceptance forms the gentle center of the topic, where uncertainty sits alongside well-established features without tension. The images of halos, filaments, and clusters soften into broad impressions. The details of density profiles, subhalos, and particle properties fade into the background. What remains is the steady sense of an unseen mass, shaping the universe in quiet, consistent ways. The motion of stars, the bending of light, and the growth of structure all reflect this presence, forming a simple, coherent picture. As the pace slows further, the narration settles into a steady stillness. The vast structures shaped by dark matter stretch across space without haste. The unseen mass remains stable, moving through cosmic time without losing its form. The quietness of this behavior brings a sense of calm, where the unseen becomes a gentle part of the universe's foundation. With the inner region of understanding reached and the patterns of dark matter resting in place, the narration drifts into silence, carrying the steady calm of the unseen mass into the quiet of rest.